So people may want to mute themselves. I'm recording and welcome. This is the Virtually Makerfaire special edition of the Introduction to Quantum Computing classes. And I've seen some people, I've recognized some names here that's dialed in, and welcome back. This will be a revision for people who have already been taking the classes that I've been hosting on Hackaday. But the purpose of this class is also to get people a quick start with quantum computing, and then they can quickly catch up and be able to join some of our more advanced classes. And this is, I got started with this project when pretty much aligning with the time when we started working from home. And it just came to my mind that I wanted to do some creative work, but also be able to explain quantum computing to people. And I've always been drawing, so I thought that probably should be a good challenge for me to combine the two. And then ever since I've started giving this lecture on Hackaday every Sunday, there's 30 minutes that I discuss a topic. I don't try to overload people with information, so have like one concept, either it's theory or hardware or about programming. We have 30 minutes, and then I usually leave some time for people to ask questions. So people who have been to these classes know that you can feel free to message in the chat, and I may not be able to get to it when I'm talking, but I will try to leave some time to come look at what people have written here. And also when that starts, people can unmute themselves and ask questions directly too. So here are some of the links that people can follow. You can search on Hackaday for the weekly project and comic update. Also, I've been using the quantum computing materials from Microsoft, both the documentation and the quantum katas that we develop as exercises. Just zooming out, our world has been running on computers, and the reason we can be connected right now through the internet is because we have all these data centers, everyone has a computer, and everything is run by algorithms and automation, and of course there are people, but we're using machines to help us with our work. Pretty much everywhere in every industry is using intelligence and high tech. However, there are still some of the areas that even the most powerful supercomputers cannot solve. Things like, or they can solve but run into fundamental limitations. So things like chemistry simulations or discover materials, those are fundamentally quantum mechanical interactions that we want to study. And there are things like logistics or signal processing, information security. Those are what we made up as our most efficient way to collect data and get insight. But still, our most powerful supercomputers may still run into limitations in the way they run algorithms. And we can get inspired from quantum mechanics to solve some of the areas that are not fundamentally quantum mechanical. So there are quite a lot of applications in quantum computing. And in a way, quantum computing is really a biomimicking, is like a lot of the other inventions that we created as humans. We are using the fundamental laws of nature to build computers that run algorithms that's specific for this type of hardware, so that we will be able to solve some of the most challenging problems that our best computers, best classical computers still run into problems with. So I would give people an overview of how quantum computer works, from the theoretical background to some overview of algorithms, and also give people an idea of the types of hardware that we've been using. We're well familiar with all kinds of counting systems, the way we capture information. We can describe time, numbers, and money in all kinds of systems. But eventually we resolve down to using transistors in our electronics. All our modern computers and electronics are based on the building blocks of transistors. So they are basically tiny switches that can be on and off. So that captures the classical bits 0 and 1. So classical bits is limited to binary. And in a way, we artificially make it binary so that it's easier for us. We can turn a switch on or off. And if the temperature is too high or too low, if we flip a coin that is head or tail, these are all kind of examples of binary systems. And we can use classical bits 0 and 1 to describe them. And on the right here, these are the states that we can mathematically describe in terms of a 2-by-1 vector. Is a convenient mathematical way to describe the bits. So right now we're still just talking about classical bits. And when you have this binary system and you're using a 2-bit basis, these are the two possibilities that you could have. The way to achieve that in computers is using semiconductors that you can sandwich semiconductors with insulators and metals and create transistors so that you can form a 0 and 1 or off or on using the electrical flow in your material structure. When you have electricity, just simply speaking, from source and drain, you can call it a on. So it's a 1. If there's no electricity, you can adjust that by applying the gate voltage. Then you have a off. But we don't have to do it that way. That's a convenient way so far for us to do calculation, to capture information. But nature fundamentally does not behave in a binary manner. We know that the fundamental particles, like electrons or photons and atoms, they all behave. If someone's not muted, would you mind muting yourself? And we'll have time to have interactions after this big, quick crash course. So in nature, these fundamental particles, they behave in a completely different way. They're not just zeros and ones, but they have energy levels that they can sit on. And all these energy levels can be in superposition. So this is one of the biggest, most important concept people need to understand. What is superposition? Let's take a look at the difference between classical bits and quantum bits again. And oftentimes people would describe superposition as a 0 and 1 at the same time. But please do not say that. It's not really the correct way to describe superposition or qubits. If you look at this picture here, classical bits, you can have a very clear cut. You can have a circle. If it's empty, you can label it as 0, or fill, you label it as 1. But a qubit could have this combined phase where you can represent a circle with 1/3 of 0 and 2/3 of 1. A qubit describes that kind of state. Or you can have a lottery thing that has like 20 bits inside, and you can drop out if all of the 20 bits are 0, you can label it as 0. Sorry, all of the 20 bits are red, you can label it as 0. But if all of them are blue, you can label them as 1. So all these are pretty arbitrary. You can come up with systems that can describe this absolute state or condition or status of your system. In a quantum bit, you can mix up these colors, and perhaps you will have 8 out of 20 of them being 0, 12 out of 20 of them being 1. Same as this coin metaphor. Head could be a 0, tail could be a 1. But if it's a spinning coin, you don't know which side it's going to land on. You could have, if it's an even coin, you could have 50% of chance of landing on 0, or 50% of the chance landing on 1. These probabilities are what quantum bits describe. It's not 0 and 1 at the same time, but they are states that have probabilities associated with them. A spinning coin is like a qubit in a way that when you're spinning it, you don't know which side it would end on, but you know the probability of either head or tail, if you know that. So mathematically, you can write out a quantum bit still in the form of a 2×1 vector. And now you can see that it is a linear combination of our previously introduced classical bits, 0 and 1. But the A and B here are amplitudes that are associated with these possible states. And the amplitudes here can be positive or negative or even complex numbers. All we require is to have these amplitude squared, modular squared sum to be equal to 1. And what does that mean? It is really to show that here in this 1 qubit, you have these 2 probabilities. And by common sense, we know anything's probability should not be larger than 1. So this is all it's about for a qubit, is you can label them with an arbitrary equation like this, and each possibility has an amplitude, and their amplitude squared describe the probability of each of them. So on the right here, you can see in our previous example, in that circle example, we know that a squared is 1/3 and b squared is 2/3. Similar with the other metaphors. And you can come up with all kinds of situations like this, where you can have a mixture, a linear combination of possibilities. This is what a qubit is. When you have multiple qubits, you can mathematically combine them. And for this class, I try to reduce as much math as possible. So there are some equations, but it's not going to require you to really derive them. And at this point, if you can just get a sense of the concept, that would be great. And we have a lot more opportunities to learn. So when 2 qubits happens, you can combine them with a tensor product. And all it does is to describe all the 4 probabilities that a 2 qubits can be in. Just think about it. You have 2 qubits. Each of them could be 0 and 1. And when you combine them, there are 4 configurations they can be in. So each of the 4 states, possible states, would have their amplitudes in front of them. And again, this normalization condition, which is formally called, is that their probabilities are adding up to be 1. That's it. So when you have more qubits, you would just do the same kind of mathematical combination. So again, we have classical bits, which are either 0 and 1, but quantum bits can be a linear combination of 0 and 1. So I've already described that each of the possible states could have an amplitude associated with them, and their square is the probability. Then what does this lead to? Say you have 1 qubit, you will have this first configuration. On the left here, you can have the state having some probability of having a 0 and some probability of having 1. And A and B here are both arbitrary numbers, could be positive, negative, or complex. When you have 2 qubits, as I showed earlier, you will have these 4 configurations. When you have 3 qubits, you will have then 8 possible configurations. So see all the 0, 0, 0, 0, 0, 1, 0, 1, 0. These are all possible states that only 3 qubits are needed to represent. Then when you have n qubits, you will have 2 to the n possible configurations in superposition. That is very powerful. So the number of possible configurations your state can be in scales exponentially with the number of qubits. It's not just you can have 2 to the n, but the number of possible situation or state your system can be in is infinite, because each state has an amplitude, and the amplitude can take up any number as long as you know the sum of probability is 0. So the amplitude can be positive, so 1, half, 1/3, 1/4, etc. Could be negative, so -1, -half, -3rd. And these are 2 real numbers examples. But they could be imaginary numbers too. You just add an I in front, so it makes it imaginary. So in general, the amplitude here can be really any number. So then what is the consequence of this? From our everyday experience, we already have experienced many different kinds of amplitudes, like water waves or electromagnetic waves. We know that when amplitudes have the same phase, they can add up. So you can enhance, you can have this called constructive interference between 2 waves, and they can add up. But if they have opposite phase, they can subtract and cancel each other. This is called a destructive interference. Then why is that helpful? How are we using that in quantum computing or quantum mechanics? If we ask a question, a probability question, what is the likelihood of getting sunny weather the day after tomorrow? If you describe this question and trying to get the answer using this tree diagram, which we learned when we were kids, what's the probability of being sunny or raining? Say we have 50-50 chance of getting either. And then going to the next tree, next branch, it could have another split. So when it's 50 sunny, then you could have 30% of sunny and 70% of raining. But if it's raining, maybe you could label, these are just arbitrary numbers you can come up with. So to know the probability of getting a sunny day the day after tomorrow will be timing all these probabilities down the tree. So 50% times 30% plus 50% times 90% will be 60% chance if you describe the system in a classical way. But however, if fictitiously this situation is quantum mechanical, then there's nothing preventing us from having a negative amplitude, because we just need to make sure that the probability add up to 1. So amplitude square is probabilities. There's nothing preventing us from having a negative amplitude, because when we squared it, we will still get a positive probability. So just for the sake of argument, we label one of the branches as negative. And what happens is that if you then time down the tree through amplitudes and then get the ultimate probability, turns out even having this extra branch of having a sunny weather can reduce the probability of having a sunny day in 2 days. Because math, you see the number comes out as only 8%. So this negative sign is destructively interfering with your first branch. This is what quantum mechanics and quantum computing is interested in, is that is utilizing this interference pattern. And this is what we would measure. When we do a measurement, it is the result of interference that we obtain. You could have situations where you have many constructive interference happening that increase the probability of you getting this result. But if you have a destructive interference, even if you have the probability of that state, it may be canceled out. This is what actually happens when you have measurements. A very famous and well-known example is this double slit experiment. You've probably seen it sometime in your student career. If not, don't worry, I'm walking you through that. It's an experiment using some quantum particles, for example, electrons, that you can shoot them in a beam. And you want the beam to pass 2 slits. So you block everywhere, but have 2 slits for the beam to pass through. See, if you just start with 1 slit, you block one of them, you will see a distribution of electron beam passing through this slit. And you will have mostly of the electron mostly landing in the center of that slit. Then you will think, okay, if I unblock the other one, I may see 2 peaks. But that's not what happens. In fact, when you have 2 slits both open, you will have this constructive and destructive interference happening, which gives you this interference pattern where the center turns out where you actually have a block would show a peak. And near these slits, you may even get a destructive interference that has a low probability of having electron beams landing there. This is what's strange about quantum systems. And they are enabled by superposition. And superposition enables interference. And these are 2 of the most important concepts, superposition and interference. But there's something else. And before I go there, I also wanted to show that mathematically you can describe the measurement. Say if you had 2 qubits, and then you will have 4 probabilities. But then if you measure your first qubit and it turns out to be 0, you would know that the probability of getting that is described by their amplitude square, and the probability of the first qubit being 1 are all gone. And then you left your system with this new state that is described by these 2 possible states. And oftentimes people describe this as a collapse. They say this is the Copenhagen interpretation of measurement. It was an easy way out for physicists back then who were still trying to understand what quantum mechanics was, and they didn't quite know about the interference. They didn't think that way, and they thought, okay, we can just say it collapses and the other probabilities are gone. But now we know that is all what the amplitudes and the interference doing to measurements. So I actually prefer, I still see people use the word collapse, but I think we can avoid that. The other interesting thing that's enabled by superposition is entanglement. Remember that colorful diagram I showed earlier? If we had 2 qubits, we could have these 4 probabilities. But because of superposition, we could also manipulate them to have those states to be in a superposition of either 0, 0 with some arbitrary amplitudes in front of them, or 0, 1 and 1, 0. And they are very special because if you just look at the form of these states, if your first qubit is 0, so if you compare just the first and second qubit in the 2 superpositions, the first one, if it is 0, the second state, the first qubit is 1. So these 2 are guaranteed to be different. And then these 2 again are guaranteed to be different. Same with this second option. You will guarantee them to be different for the first qubits in these 2 superpositions, and the second qubit will be different. Turns out that these are entangled states, which enable a very interesting outcome. But before I show you the next slide, I want to clarify one thing. When people talk about entanglement, you often will hear in popular media, when you have 2 qubits entangled, if you change one, the other one will instantaneously change, even if they are separated far away. That's a wrong statement. Please stop saying that. So when you have 2 qubits entangled, when you change one of them, the other one doesn't feel a thing. The other one, there's no spooky interaction between the qubits. And when they're separated far away, they are still entangled, because entanglement does not have dependency with distance. So of course, if you separate them, even if it's infinitely far away, they can still be entangled. But what does entangled really entail is that the 2 qubit outcomes will be correlated. So let's look at these special states called the Bell states. Those are 4 possible states if you just give them equal probability. So this sign could be, so the amplitude could be minus, so you could have these 4 outcomes. So all these superposition states are having equal probabilities of existence, and they could have plus or minus in between them. What happens is, let's say, if you take the phi plus, it's just arbitrary label, take that as our state to look at. You measure the first qubit. If you get 0, you will know that there's no possibility that the state could be in this 1, 1 anymore. You will know that you will end up having 0, 0 with a probability of 1/2. So this is saying that even if you didn't measure your second qubit, you will already know what your outcome of the second qubit is. Say if your first qubit is 1, then there's no probability of this state contributing. It's all from this state. So you would know you will end up having 1, 1 with a probability of 1/2. So all what entanglement does is to show that if you measure 1 qubit of one of the entangled qubits, even if I don't measure the other one, I know what the other one will come out to be. That's what this entanglement and this special Bell states are enabling. And just by measuring 1 qubit, you will know the probability and you will know what the other qubit will be. That's all what entanglement is. There's no spooky interaction. There's no poking one qubit and changing the other one. No. So what this could enable is to help with communication and encryption. Say if you start with some Bell state, and then because you entangle two qubits, you put them in a Bell state, and you separate them, give it to Alice and Bob. They can go as far as they want. You have Alice measure her qubit. If she gets 0, in this case, she knows Bob will get 1. And if she wants Bob to get 0, then she will maybe call him or email him, tell him, hey, do some manipulation to your qubit and you can get 0. So she would know what Bob will get based on her own qubit. Of course, if you can entangle 2 qubits, you can entangle 3, you can entangle infinite number of qubits. A common mistake I already mentioned is when people say you change one, the other one will instantaneously change. And what law is it contradicting? Is contradicting the fact that nothing can travel faster than light. If you can change one qubit and the other one immediately change, that would imply information would travel faster than light, and that's not allowed. So there are a lot of other common mistakes in quantum computing that especially media talk about all the time. There's a list. You can, if you're curious, you can take a look there. Even if you cannot communicate faster than the light, it could still be useful. Like in communication case, you can make qubits as your encryption keys, and you would know what information the other person will receive based on your own qubits. So you can make some useful cases still out of it, even if it's not communicating faster than light. So entanglement can be very useful for us, but it can also mess things up, because all of the systems that we're looking at depend on this intricate interaction between very, very tiny fundamental quantum particles. You have to be very careful that anything you introduce to your system can interfere with it, and it can entangle with your system. So when you do a measurement, you're introducing a measurement probe. That at an atomic scale is also quantum mechanical. So that measurement could also introduce an entanglement and break your original qubit system, their entanglement. And this interaction, this messing up is called decohere. So we have to make sure that when we do measurements, we are accounting for all of the things that could happen and do it very carefully. Now, here are just 3 concepts that you have to not have confusion with. Superposition and interference and entanglement. Interference and entanglement are both results of superposition. And interference, can someone mute themselves? Thanks. Interference is what causes measurement result to be what we measure. And entanglement is a result of entangled qubits being correlated. So these are the 3 key concepts you just have to understand about quantum computing. So nothing really demanding is required. Like we haven't talked a lot about quantum mechanics, and I haven't introduced too much math so far. So these are the 3 things we have to clarify. Then we will think about how to manipulate qubits. In a graphical way, we can always label a number as a real number. We can draw a line is in 1D, and this is a real number. You can also graphically represent a complex number, having this complex phase introduced and in this x and y coordinates. Just mathematically, you can describe our system. Now, when we have a vector, we can represent it also mathematically, including these direction this vector is pointing to. So overall, it looks like a sphere. And anywhere on this sphere, you can have a point that tells you the direction and the length, and it describes this vector A and B. So here, in terms of qubits, we know a squared plus b squared is 1, and the length is fixed. The total length of this vector would lie anywhere on this three-dimensional sphere. But in fact, this topology, this sphere is actually 2D on the surface, and that's why we only need a sphere, a 2D object, to describe a 2D vector, so A and B. Anywhere on this sphere, we can label them with these two angles. So this is actually, if you look at the form, this is our qubit. This is some amplitude times 0 and an amplitude plus 1. In fact, we can visually represent this quantum state, a qubit, using a sphere, and it has a name, block sphere. What we do then, if we want to manipulate the qubit, is nothing but changing the angle of this vector on the sphere. So on the block sphere, you can label your 0 as the top point along the z-axis and 1 at the bottom of the z-axis. And an arbitrary state would then have this mathematical description using the angles theta and phi. And we know that 0 and 1 are nothing but special cases when theta is 0 and 180. That's where we can put the point here and there. And what a gate does, the name comes from the same classical algorithm like logic gates. We also have quantum logic gates. What a gate does is to manipulate qubits. It is an operation you can apply to your qubit system. Because we can write out and represent a vector using this, your qubit using this vector, you can apply a 2x2 matrix to change the vector. In fact, there are some generalized matrices that specifically can change the angle phi and change the angle theta. So these are the arbitrary gates you can use to change the vector. So this is how mathematically you can manipulate your qubit anywhere to change these states anywhere on this block sphere. It's also a bit like the set of coins, again, using coins as metaphors. Here, the theta and phi can be really any number to have the point anywhere on this sphere. So then you get infinite possibilities. But for convenience of computing, we want to have a set of gates that will put the qubit in some specific places. It's like a set of coins where we are not trying to have 1, 2, 3, 4, 5, 6, all of the numbers represented by each coin. We would just need a set of minimum number of coins where using different combinations, we can have a number represented. Similar idea for quantum gates is that we want a set of gates where you can combine to put your vector on some specific convenient places on the block sphere. Here are some commonly used gates. We can have these, because we are just changing the phi and theta, we can have a gate that just changes, rotate the phi. This is called a Z gate. is rotating the vector around the z-axis by 180. So you can write a 2x2 matrix like this. I would recommend you go back home and try the math to see what happens when you apply this gate on a qubit. Just pick a simple one like 0 or 1 to try it. We can also rotate x, which is changing theta, and that is by this x gate. So these are just two of the very commonly used gates that's rotating around the axis. And you say, oh, how do I rotate around y-axis? Turns out that you can actually do that by combining z and x. So you actually just need these two gates to rotate around different axes. There's also an important gate called the Hackaday gate or H gate. It has a form like this. So it's almost like 1111, but here is a minus sign here. What it does is that when it applies to 0, it will make the gate to this diagonal location on block sphere, and we call it a plus state, which is nothing but a 0 and 1 in superposition with equal probability. But if you start with 1, the H gate would make it to the opposite point on the block sphere. We call it minus state. You can try this at home and you find out that this minus sign is very important, because without that minus sign, you would not have this minus sign, and you would not be able to distinguish 0 and 1 once they're in this diagonal place and you apply a H gate, you will not be able to get back to distinguish 0 or 1. So this is a symmetrical basis to the original 0 and 1 basis. When you do a H Hackaday gate to a plus and minus, you'll be able to get back to 0 and 1. Of course, there are other you can reduce the angles of rotation by doing more finer division of your rotations. So here are some other states that are rotating by different angles around the z-axis. You can have a lot of different kinds of gates, but here are some of the common ones that we use in almost every algorithm. But so far, we've only been talking about a single qubit manipulation. What about having multiple qubits? An important one is called the C-NOT, is a controlled NOT gate. If you're familiar with classical logic gates, a NOT gate is a flip. Here we have a control. So what it does is that it depends on the control qubit. If it is 0, the target qubit would not change, will have no effect. But if your control qubit is a 1, your target qubit will be flipped. And this is really expressed through this matrix here. You can see that first quadrant there is preserved, is an identity matrix, and is having the control qubit preserving the target qubit. But then the fourth quadrant is a switch. So it would change one when the first control qubit is 1. So again, try this at home. You will see this will be the case. So block sphere was very useful to represent 1 qubit, but you see that we can't really do much about it because as humans, we can only see maximum 3D. And when we have multiple qubits, is multiple dimensions beyond 3D. So we can't really use a block sphere to represent 2 qubits, and it's not it's not going to be helpful. But we can still visualize things graphically. When you have multiple qubits, now we can use a circuit representation. All it does is to describe the change of a qubit over time. So you use a line. It's like in music, you have lines that describe, that tells you that the music is evolving. But here, instead of notes, we have gates that will be applied to those lines. A C0 is described as a control on the top and a qubit at the bottom. Oh, you can reverse it too, it doesn't really matter. But the dot is identifying the control bit. And this circle cross is your target. So what this says is you do a C0 between A and B, and your outcome will be A, but the second qubit would be target B controlled by A. If you just search online, you'll find all kinds of gates. We describe a few that's very commonly used. And you can see that all of them can have a circuit representation with a matrix to mathematically tell you what happens to the numbers. And a key point to differentiate is that the gates are reversible. When you apply a gate to a qubit, it makes sense if you apply that again, it should be able to go back. So you want to have your gates to be reversible. They can take all kinds of forms, numbers in matrix, but you have to make sure that the form of that matrix gives you a reversible operation. Measurement is not a gate, and it is not reversible, as we previously mentioned when people like to use collapse, but really is an outcome of interference. And we do also have a circuit representation for measurement, which looks like a dial. After the measurement, there's two lines. It tells you you get a classical information output. So that's it. You can use circuits. You can draw lines and put gates between them to construct an algorithm. This here is a teleportation algorithm. Right now, I don't we don't need to really walk this through step by step and understand the maths, but I'm just trying to show you that a teleportation is a simple circuit you can draw out step by step. And what it does is that you can have Alice and Bob prepare an entangled state. So these two gates give you an entanglement. Then Alice obtains a new qubit. She wants Bob to know what it is, but she cannot tell him directly what it is. So she wants Bob to reproduce her qubit. So how she does it is to entangle her own qubits and then do a measurement to her own qubits, both of them, and tell Bob then, hey, do this to your qubit, and this is what you will get. So this you can do with circuits, and here is giving you a very important construction. Having a H and a C0 will give you, and that's how you entangle two qubits. So you thought, okay, we can draw things nicely with circuits for all the algorithms. Yes, for simple algorithms, but when you have a lot of qubits, a lot of them, it will get very messy. And it's not really scalable to always use circuits to do your actually useful algorithms. So then we actually need computer programs, specific language written for programming quantum computers. So I work at Microsoft, and we have come up with a quantum language called Q#, where we can just use high-level definitions of the gates using code to write out all of the actions and operations we want to apply to the system. So in terms of algorithms, we don't really have time to go over them, but I will give you a very quick overview. When it only had a couple decades of development, really, the quantum computing has developed really fast. And when it was first proposed in the 80s, there were some development in proving that we could develop quantum Turing machine and have universal quantum circuits. And then later on in the 90s, Shor's and Peter Shor and Groover and a bunch of other algorithms came up. So a lot of algorithms are developed based on Shor's and Groover's algorithms. Peter Shor's algorithm is to do factorization of really large numbers. That's very efficient and can be more efficient than any classical algorithms to do the same thing. And also, our RSA cryptography is based on factorizing our classical computer not being able to factorize really large numbers. So if we had quantum computers to do that, it can just break the RSA encryption very quickly. So that's why a lot of the industries that rely on security are already looking into using quantum computing to. It would break, but they would be able to use new algorithms to come up with better security methods. Groover's algorithms is a way to do a search in unordered list much more efficiently than classical algorithms. So we actually have been talking about these algorithms in the Sunday classes I've been giving at Hackaday. So we have introduced the oracles and talked about Deutsch's algorithms and Groover's algorithms. And so there are other interesting algorithms we're going to look into. We don't have time for, but don't worry, because it is not quantum computing would take a lot more than an hour of talk. So we have these weekly weekly classes at Hackaday. Here are the links. Every Sunday, today is a special case. We moved this time to align with the Makerfaire, but usually it's Sunday, and I have 30 minutes discussing a simple one concept, and gradually people build up their skills. And I'm very happy to see that people are already writing quantum programs. We use the quantum katas, and I have the certificate that I give out to people. They can complete any quantum kata and take a screenshot that they completed it. They can tweet it, and they can post it on LinkedIn and add these tags so that we see that I can see that they have done the work. So some people already got the certificate, and here's Tom who printed this vector graphic certificate onto a mug that looks really nice. And this is kind of a modification of Hackaday, but here is Schrodinger's quantum cat. So come to the class and also try the exercises. You can also submit your completions to get certificates. A quick rundown of hardware. We don't have a lot of time for that, but as I mentioned earlier, that classical computing is based on transistors that are functioning like switches. But for qubits, we need a system that can have two states that can be put in superposition. So natural quantum systems are already like that, but we need to be able to use two of the states. So an electron can be a natural candidate. It has spin up and spin down. Maybe we can use them as our 0 and 1 states. But then how do you capture electrons and control them? There are a few different ways. So in semiconductor stacks, you can have two semiconductor layers and have a layer of electron sheets confined in 2D. And then you can apply metal gates to even drain out the electrons around the gates to form a quantum dot in that little region that can keep just one electron in there. And then you can shine laser light, or you can manipulate the spin of that electron there. Or you can have a crystal lattice. Say you have a diamond, you can have 6 electrons in there. You take out one of the diamonds and actually take out 2 and insert a nitrogen that has 1 more electron. So that actually electron gets trapped between that nitrogen and vacancy region. So that's another way to trap and manipulate electron, but they're very hard to scale. There are other ways to scale. If you can use electrons, you could also use iron spins. So you can make traps of irons that will have spins that could be aligned to your electromagnetic fields. This is a very simplified version, but really you are using the energy levels of these electron spins in your irons, and you are using two of them as your 0 and 1. You can shine laser light to move them and flip their spin. In that way, you can control them. If you can trap the electrons this way, you can also, or use ions and atoms, you can also form artificial items. Things like LC circuits that you can fabricate on your silicon chips. You can actually form a, if you know if you know the LC circuits can be a oscillator, then you know that they can have, if they are made small and cold enough, they will have all these discrete energy levels your system can sit on. And you can use some superconductors as your inductor component to form a energy state that looks like this, and it has uneven levels. You can use the very bottom two as your 0 and 1. So just some simplified picture for you. But then think beyond that, you can even use things like photons. You can guide the photons and assign polarization of photons as your 1 and 0. But Microsoft is pursuing something very interesting and different, which is using a topological architecture using a nanowire on superconductor that can form this special modes for electrons. When electrons occupy those states, you can say it is a 1. If they do not occupy them, it could be a 0. Just a very, very fast blazing through this hardware. And I will end the class. I think we probably don't have time for questions, but we can have the questions in the Hackaday project. Feel free to comment and write in there in the comment section. A question I get very often from people asking how they can learn quantum computing. I think there are several stages. So in terms of concept, I already mentioned that you just need to really understand what superposition, interference, and entanglements are. And that's basically all you need to know in terms of concept for quantum computing. And then you need some linear algebra, but you don't have to be super good at maths. It's just that you need some matrix multiplications and know about complex numbers. But I think it's more of a mental barrier for people rather than the ability to do linear algebra. So if someone don't believe they can understand this, really a comic book cannot help. So the mental barrier can be passed. And when you look at algorithms, you really have to develop the habit of zooming out, because the math, people can get really lost in the math, can get really lengthy. But all you need to do is zoom out to look at how is this algorithm really using superposition, interference, and entanglement. So to get an intuition. Then the hardware is the only topic, only area that you really need condensed matter physics. So unless you're really pursuing hardware, you can do the other three. Again, these are the information. This is recorded. I think I would upload it on YouTube and also on Hackaday project. You can find the links. One last thing. We just produced 2 Microsoft Learn modules. One is to help you get hands-on, get started with programming your first Q# program using the Quantum Development Kit. Is very easy, so take that class, take that hands-on exercise. We have also one module called the Solve Optimization Problems by using quantum-inspired optimization. So this is another area that's we didn't talk about, is using quantum behaviors we get inspired to apply to classical hardware. So these are the two available on Microsoft Learn. Take a look at those. And I would also love to hear your thoughts on what you love to learn. Okay, so this is my next talk. I will go and dial in. And I think I'm a little late, so I will look at people's messages here and I will also put them in the Hackaday. If there's any question, I'll add them there. Thanks, everyone.